Any newbies to the Nurture Nature Center? Any new people? Welcome, welcome. You can see we have a beautiful art exhibit right now going on. It's called The New Mimesis. It's showing work from 17 artists about biomimicry. So after this presentation, if you want to take a look, it's in this room and also in the room across the hall, which is our sphere room. And we have a beautiful Science on a Sphere exhibit there too, if you haven't had a chance to see it. And we also have a new hands-on sandbox. You can get your hands into the sand and see how landscapes change. So that's a really neat exhibit I would encourage you to go see. We as Nurture Nature Center got started in response to flooding. So if for those of you who remember, in 2004, 5, and 6, Easton flooded in a very short amount of time. There was this repeat flooding. It can happen. Rivers flood, they have a floodplain, it's their real estate. It's natural cycles, and we wanted to bring this issue back up because when it's been 10, 11, 12 years, we tend to forget. And one of the things that happens is we don't become prepared and we don't have our plans in place, and we forget that if we develop along the river that we have this risk of flooding. And so we wanted to bring this back up to the public and to the city of Easton officials and other members of our community to have this discussion and remember that we are a community by the rivers. And the rivers are beautiful and they give us a lot of resources, both aesthetic and physical, but we also have to respect their nature and their power and learn how to live by them peacefully. So we are very fortunate to have two experts here. Dru Germanoski is from Lafayette College, and we also have David Brandis, who will join us in a little while from Lafayette College as well. They're both professors there, and I was at some of the lectures that they provided last semester at Lafayette, and I thought their talks were great. And I thought that together they provided a really comprehensive picture of flooding, the nature of flooding, and also for our area what that means and how we can be prepared. So I asked them to come join us, and we have a great seminar for you today. The talks will be about 30 minutes each, and then we'll have time for questions and answers. So if you have any questions, please feel free to speak up and ask. As Nurture Nature Center, we continue to do education about flood risk and preparedness, and we also have a lot of grant work where we try to help the National Weather Service improve their products so that the public can better understand the flooding potential. So if you're interested in any of our other work, I'd be happy to talk with you after the presentation. But without further ado, I want to turn it over to Dru to start.
Okay, do I need this?
No.
I think I can get away with that. Okay, so, I hear it now. Okay, so yeah, this was part of a semester-long project at Lafayette Confluence, interdisciplinary program associated with rivers inspired by Allison Sarr's artistic works, Breach. And so you notice there's kind of a gap up here. It used to say persistent flood hazards in the Mississippi and Delaware rivers. I backspaced the Mississippi out and took some of that out. And the way we did this the last semester was I set up David's talk on flood frequency by simply describing river flooding, types of floods and so forth, with some emphasis on the Delaware, okay? So that's where we're going. So here are the objectives. I'm gonna place flooding into perspective. I'm a fluvial geomorphologist, means I study rivers and earth surface processes. I'm a big fan of understanding rivers in their natural context, and I'm not a fan of flood control, and I never use the word flood prevention because there's no such thing, okay? People say flood control, engineers say flood control, people hear flood prevention. There's no flood prevention. So I want to talk about various types of floods. How do rivers flood? Considered a flood hazard in Delaware River, and then I primarily too want to set up David's talk on flood frequency analysis. For some reason, I don't know why that's dropping off at the top, but this basically is putting, flood perspective in river form and function. So here you see a river at about bank full flow in the Midwest. The flow is within the confines of the banks. here you see a river that's flooding. And you can see by these natural levees here the configuration of the river. So discharge here is exceeding channel capacity. So here again our home rivers flow within the capacity of the channel, and then the home rivers with, most people view this as some unexpected event. I just simply see a river utilizing its floodplain, okay? And us having gotten in the way. Something to put this into perspective is understand how rivers get the configuration that they have, because we somehow think that that's unnatural, but in reality these are low frequency, high magnitude events, right? And so when we think about what determines the form of a channel, during today, for example, the river is flowing through an inherited channel. It was inherited from a higher flow. A lot of data, and I'll show you some in a minute, show that the channel forming discharge, the flow that determines the cross-sectional geometry of river channels, is what we call about bank full, a less than flood full event. And the reason for that is, and we see this over and over, is for a channel to change its configuration, it has to mobilize boundaries. And in most systems, something close to bank full provides enough shear stress to mobilize the boundaries. These events therefore have enough energy to develop their geometry by moving sediment, and they also occur relatively frequently. Most rivers, particularly in this climate, have a bank full discharge of about occurring every once, maybe once a year, every couple of years. That's what the overall long-term frequency analysis shows. Okay. Flooding, of course, is something above that, and those are lower frequency events, right? So there are a whole variety of discharges that we would consider as floods. Something else that David will bring out, that the concept of the 100-year flood is in some ways terrible, because the 100-year flood is simply a flood, or the 1% flood, is a flood of a particular size. It's not a measure of the frequency with which flooding occurs. So in a system like this, it could be, that's the 100-year flood. And the point being, there's a whole other range of flows. They're flood events, but they're not the 100-year 1% flood. So this data is just a simple presentation relating the overall channel discharge, and this says bank full discharge up here. So bank full discharge across, and just simply showing for a variety of rivers, some in Pennsylvania, others, a variety of data sets. But what we see, the take-home message is simply this, that for a multitude of rivers, we see that the channel width is related to bank full discharge. So there's a good relationship for any particular bank full discharge, for any particular river. Generally, there's a good relationship, and same thing with depth. So this is a bit of data. There's scatter, but basically illustrating this idea that bank full flow is the one that determines the geometry of a river, okay? And so when we think about a river and its overall environment, then we focus on the channel on that last diagram, that last data set. Most people would look at a photograph like this and say, there's the river. I look at a photograph like this and I say, that's the river, okay? That's the floodplain. The river created that. All of the landscape here consists of sediment deposited by that river. And this next cartoon, I think, does a better job of contextualizing that. When you think about it in that perspective, it's a little bit more obvious to see that we're dealing most typically with a river valley carved in bedrock, flowing through material we call alluvium, material deposited by a river, and those deposits occur from the rivers migrating back and forth, cutting off bends, flooding and depositing material on the landscape. And now we live in such an artificial environment. Most floodplains, you don't see swamps on them. We've basically filled them in. And in the Delaware River would have been something that looked a bit like this. It's a composite morphology. It has islands in it that are still inherited from its glacial history. Now, just to show you, you might say, well, I don't know if I can't see that in downtown Easton. And so here I'm just saying the floodplain is a part of the landform the river created by the rivers, and rivers utilize that during floods. So here's downtown Easton. This is where the new city intermodal garage is, and the material up here that's lighter colored is all fill. You can see some bricks and pieces, but these rounded cobbles down here are alluvium. That's material deposited by the Delaware River. All of downtown Easton is underlain by these materials. So the Delaware River is no different than that, with one exception. To be fair, those gravels were deposited 20,000 years ago during the last glacial maximum, when there was glacial ice right at Belvedere, New Jersey, and the Delaware River was a braided multiple channel sand and gravel high energy river system. But the area we consider riverfront property, I consider floodplain and a river valley floor. Okay, so it's kind of it's embarrassing to admit this, but I do rely so much on the things I have written here. I thought I'd be seeing them, so there's some little glitch here. I apologize for that. But what I want to emphasize here is that flooding is not an unusual event in any river, certainly not in Easton. You look at these photographs and you can tell these are multiple different floods, right? You see snow. This was January of '96. You see snow down here on the 3rd Street Exxon station. You see leaves on the trees here. Some of the photos you'll see won't have leaves on the tree nor snow. So floods happen very frequently. Here is data from the Belvedere gauge on the Delaware River, flood stage showing here in red, and various events that represent floods of various size. 2003 of October, March of '36. This was, of course, there was big flooding throughout Pennsylvania that year. There's our flood of record, Hurricane Diane in August of '55. The 3 events that Kate mentioned a few moments ago, Ivan in September of '04, the April of '05 flood, the June 2006, 3 floods right in a row. Irene in 2011, that was the rain on snow event in January of 1996. So floods are, infrequent, but frequent enough. And, none of these are exactly the 100-year flood. Okay? And these events here, I never forget this. Here I'm being taped today. There was one time in my life I wish I were taped, and that was in I think it was November or so of 2004. And the river flooded, and we had a meeting up on campus. Fred Quiviar, then treasurer, was conducting it. There were city of Easton officials, and they were talking about college development down on the Bushkill and the floodplain. And Fred said, well, we're good because we had the 100-year flood in 1955, and we had it again in September, and we're good. And I said, Fred, that river could flood again next year, and that river could flood again the following year. I never told, apparently, a funnier joke. The whole room erupted. There may be some people slapping their knees. They were laughing. So you geologists say the funniest things. And again, it's this concept that every flood's the 100-year flood. You've probably all heard people say that we had the 100-year flood 3 years in a row. None of them were the 100-year flood. They were just floods. Okay? So just to illustrate other rivers, to just convince you that this is what rivers do. Here's the Indus River in Pakistan, and one of these, that was 2009, 2011. There's 2016. We can do this over and over. The Mississippi River, that's normal. Here is the Mississippi. That's the Illinois River coming in, and the Missouri from the west. There it is in 1991. There it is in August of 1993. You'll think I just changed dates. You'll see that same image again later. 36 I mentioned, there's the big Pittsburgh flood of 36. Here's the Missouri River of 2011. So rivers flood. If we look at the Delaware in particular and types of flood, I want to distinguish between tributary versus the main stem river. So we think about the main stem trunk river and then the multitude of tributaries. And flood types are a bit different in different rivers. So these are, I'll show you in sequence, a variety of mechanisms of flooding. One type of flood we call upstream floods or flash floods. They tend to occur in the tributaries, in the small systems. They occur in response to heavy precipitation. They are, as the name implies, the peak flow comes on quickly, it's short-lived, and it's over with. And these data here are from the 1972 Hurricane Agnes flood in the Susquehanna to illustrate the distinction of an upstream flood or a downstream flood. Here's Bald Eagle Creek, a tributary to the Juniata, which is in turn a tributary to the Susquehanna. These are all the same time frame. And you see Bald Eagle Creek, the discharge came up very rapidly, hit a peak, and then it dropped relatively quickly. And you see this sort of, the discharge changes because we're going down system to bigger and bigger channels. But if you look at the Juniata River, it peaked at a later time, so there was more lag time, and the high discharge was more prolonged. And then you get downstream to the Susquehanna. Again, the peak came a bit later than the tributaries, and the peak was protracted for a long time. So a flash flood is something that's going to happen in response to a heavy precipitation event. It's going to be, as the name implies, short lag time between precip and peak, and the peak will be short-lived. To give you an example of one of these as well, if we go up into Left Hand Canyon, which is in Boulder, coming out of the Colorado Front Range in Boulder, Colorado, and here you can see the discharge, and this was in, I think, 2012, and very rapid increase in discharge, and then a rapid decline in the flow level. So those are usually in response to heavy rain. They're driven, of course, by steep gradients in the landscape and in the streams. This is a digital elevation model of the Front Range. So all of these streams up here in the Colorado Rockies are susceptible to flash floods of that sort. And so they have signs if you've driven up these canyons because of a lot of tragedy and people killed by flooding, in particular in the Big Thompson River here in 1976. It says climb to safety in case of flash flood. Those are examples of the types of flash floods that occur in those systems in response to thunderstorms. To bring this home, here is the Bushkill Creek upstream of Easton, and this is the September 2011 Irene event, and this is a steep stream in this lower portion of the system, and this is an example of a heavy rainfall and a flash flood in that system. The trunk rivers, on the other hand, are characterized by what we call downstream floods. And so it's September 11th with Irene, the Delaware River came up. It stayed at a high level for a while, and then the discharge decreased slowly. Usually in big rivers, these downstream floods are often driven by multiple precipitation events, something that we call event sequencing. So if you look at the Mississippi in 2011, there was a rainfall event, discharge came up, dropped, then another big rainfall event, high discharge started to drop, another rainfall on top. And so the notion of event sequencing is really quite important because this flow associated with the rainfall that occurred in May of 2011 would not have been above, would not have been a record high, would not have been up there at all if it weren't for that preceding precipitation event. 1-2 punch is a common theme in major floods in big rivers. And that, again, characterizes the Mississippi. We've basically seen this sequence before in '93. Here you see the same satellite image of the same place. Looks pretty much like the same flood. Normal flow, and then a response to prolonged precipitation and multiple events occurring in sequence. Again, early summer precipitation following late winter snowmelt and precipitation, and this is also again in the St. Louis area, and you see the extreme flooding in that area. Another type of flooding, what it says up there, is another type of flooding is coastal flooding. So Superstorm Sandy represents that. Rivers that discharge into oceans. When you have tropical storms and flood surge in the ocean, you get flooding associated with ocean waters coming up into the mouths of the rivers, generating flooding. That can happen in the lower Delaware. In Easton, we don't have that phenomenon. And here, for example, again, we see evidence or an example of coastal surge flooding. So it's a different type of flood than the precipitation-generated floods from upstream. This is the lower Ninth Ward in New Orleans. Katrina was, of course, an example of coastal surge or coastal storm flooding. Another type of flood is what we call backwater flooding. This tributary here is flooding not because primarily precipitation driving a flood wave down that tributary, but because this tributary grades into the master trunk river. If the trunk river floods, water will back up the tributaries and cause flooding there. So in the Easton environment, the Bushkill Creek, here's the Bushkill Creek joining the Delaware, there's the Route 22 bridge. This lower portion of the Bushkill is susceptible to backwater flooding. So this type of flooding in a tributary of this sort would be generated not necessarily by precipitation in the tributary drainage basin itself, but by flooding in the main stem river, that sometimes you see actual flow upstream in the lower part of the tributary. And here's an example of backwater flooding in the Bushkill. And as the photo kind of implies, it's pretty much accurate. The water is pretty much still there. It's not, the Bushkill's flowing from right to left naturally. This is at the site of the 3rd Street Dam. And the water's basically pooling up and sitting there as a result of flooding in the Delaware River. So that's another mechanism of flooding. So we have floods that are driven by precipitation in the upper watersheds. We have floods that might be driven at the mouth of the channel by tidal storm surges, backwater flooding up tributaries. So there are multiple mechanisms that'll generate flooding in river systems. So to look for a second then at some of these major flood events that we experience here in the Delaware River, to put them into perspective, to again zero in a little bit on what we're up against here in Easton. One of the things that we'll see over and over again is event sequencing. Okay, Diane was an event sequencing event. Hurricane Diane, if it were an isolated event, would not have been the flood of record. Every one of these events were the result of multiple precipitation or snow melt events. So here was the precursor to Diane. Hurricane Connie swept up through central Pennsylvania and rained heavily on eastern Pennsylvania and the Delaware watershed, so the soils are saturated. The stream comes up in response to that, and then Hurricane Diane sweeps through. That was the second of the 1-2 punch. I often think about event sequencing in sort of that boxing parlance, a 1-2 punch. It's not the second punch alone that might cause the knockout. It's tremendously effective because of a preceding event. In 1996, we had a huge snowpack. Those of you who lived here probably remember that. Snow started falling in December. It accumulated for literally throughout December, and then about the 3rd week of January, after more snow in January, there was a rain on snow event. Temperatures came up. It was a warm front that came in, generated rain, and we had flooding down the Bushkill Creek, had backwater flooding at 3rd Street, and we had that event. Ivan, everyone thinks of Ivan in 2004. That was preceded by a tropical storm. Tropical Storm Francis happened a couple of weeks before Ivan, and sort of that was the first punch, and there was the second one, and we had flooding in Easton. The floods of April of 2005, we had rain on snow in March 28th to the 29th, and then more rain on snow in the upper watershed, and we had flooding again in Easton. Here are data that show that 1-2 punch. Here is the response in the river at Port Jervis, New York, to the first rainfall event. The flood, or the peak discharge was waning, and then the next rainfall event, and we ended up with flooding. So we see this over and over. June of 2006, rain the week of the 22nd, 24th, and then the 26th, 28th. That 15 inches was going to cause problems no matter what. When you put that much rain on a watershed, you're going to get a significant increase in discharge, but the flooding wouldn't have been as significant without that. So if we think about the summary here of what types of floods we experience in the Delaware River here, the tributaries are all susceptible to flash flooding. The direct tributaries to the Delaware are going to be susceptible to backwater flooding. We get frontal precipitation. That can drive these floods, and especially if you get event sequencing from one rain front after the other, we get tropical storms coming up the coast. Again, and you get event sequencing, you tend to get floods. And we also get spring storms. If we think back to the sequence of the dates of these storms, they're usually late summer, early fall hurricane storms. The June were frontal and thunderstorm storms. And the August, September are tropical storms. Oh, I said that already. The rain on snow events are also spring events. And if you read the old literature of the history of the area and the Delaware River diaries and so forth, they referred to them as freshets. In fact, they relied on those to move logs down the river during those high discharge events. And then lower in the watershed, of course, the Delaware is susceptible to coastal flooding as well. So when I mentioned the persistent flood hazard, we're located in a situation where there are a lot of different meteorological events that can generate these major floods. I'm going to finish by, again, this issue of setting up the flood frequency analysis. So they flood. rivers do this. So how often? What should we expect? We use past history to try to characterize rivers. In much the same way, as a kid, I watched, baseball batting averages, right? You want to see people's batting averages to try to predict what they're going to do, or who hits well when the pressure's on in the World Series, and you sort of predict they're going to do that again. But, there's always that outlier. There's always that Cinderella story, right? Something you don't expect. And one thing I've learned as a geologist is, yeah, we can go on past history, but one thing I've learned is every time I think I know the limits of what's reasonable and what's realistic, something happens that resets the clock, and you realize, there's something that we just didn't anticipate. I never use the word impossible with respect to Earth systems. And, we can look at that record. Professor Brandis is going to describe how we analyze that record, and what the 100-year flood is. There's roughly what we consider the 100-year flood, and these other events weren't the 100-year flood. But I always think about, what about the lower frequency, high magnitude events? Never say never. What about, we have this concept, the maximum probable flood. What does that look like? It's a rather sobering thought to realize that we focus so much on this 1% flood or 100-year flood. We don't know what's in this system's arsenal. And Professor Brandis is also going to, present some information that suggests that, okay, we can use the past to try to characterize the Delaware River. What's its batting average? What's its likelihood of a home run? But is that record the same? What about the Delaware River on steroids? Does that change things? So I'm going to stop there. And Professor Brandis will tell you what the heck the 100-year flood is. Can we trust the concept going forward? What about steroids? What about changing land use and climate change? Thank you.
Forward and back. Okay, thanks, Drew, and that was a nice setup. Thank you all for coming out on this. It's a bit cold and windy, so maybe it's not a bad day to come in and listen to us talk about flooding. As Drew said, I'm going to try to sort of help to quantify some of this variability that Drew was talking about. How do we kind of wrap our hands around these floods, and sort of how do we get predictive about it and understand quantities like the 1% flood? I put a line through 100 year because that's the common parlance, but it's not good terminology. So we talk about the 1% flood, and I'll explain that relationship. Does anybody recognize this location here? Bottom of 3rd Street, up bottom of College Hill, right? So Drew showed us some sort of other shots of this area, maybe from the other side, looking out towards town. But this was a fall flood, the pumpkin flood it was called, because of the pumpkins that were washed downstream off the floodplains and came floating by. But I love this picture. I have a similar picture from 2005 with some guys canoeing through the chamois shine right over here, right? So that was kind of interesting. Okay, so let's move forward. So I think, as Drew mentioned, that originally when we gave these talks or similar talks, it was part of a series related to the Mississippi River flooding. There was a sort of a confluence of artistic work and science kind of thing that you guys do in this building a lot. And there's one remnant of that in my presentation, and it's this old map, which I love. It's an 1888 drainage basin map of the Mississippi River. And it's a neat graphic, but the piece that I kind of thought was amusing was that over here where we live are the minor coast streams like the Delaware and the Susquehanna and all of those little minor coastal streams. So we're over here trying to wrestle with conditions in the minor coast area. So an aerial shot of our lovely town, and you can see that we're framed by the rivers here, the Lehigh and the Delaware, and there's a dam here that provides water to the canal. Lafayette is up here, and there's a lot of area down here along the riverbanks. So we have to learn to live with this thing, right? Wrestle with this snake. It rears its head once in a while and sometimes 3 years in a row, right? So that's, I think that's the context, is figuring out how to properly live with a river like this. So from our perspective at Lafayette, this wasn't much our problem until about the year 2000, which is about when I arrived on scene. And now, we're developing, we have our arts campus down here on 3rd Street. And so these issues are much more immediate concern to us and our little parochial hill over there than they once were. So Dru showed some nice images of the backwater flooding in this area. Here's a couple images of flooding coming down the Bushkill. So this would be like the previous day, maybe in some cases 2 days ahead of when that backwater occurs. But a lot of energy here. You can see this is where the 3rd Street Dam is, just north of 3rd Street. And here it is rushing under what is now the Film and Media Studies building on our campus. So certainly a lot of energy there and a lot happening in these flood events that is of concern potentially, and understanding those. All right, so there's going to be a bit of overlap here with Dru's presentation, but again, I think the overall goal of mine is to figure out how do we quantify and attach probabilities to some of these events. So here we are, we're halfway up the Delaware Basin. There's a lot of land area above us, so when you think about what we see in our river, it is basically related to everything that's upstream. So what we see, the kind of behavior we see, to understand it, you have to understand the system, the entire watershed north of us. So here is similar kinds of data that Dru showed. This is we now have a gauge on the US 22 bridge. It's an ultrasonic gauge that points down at the water. And so I just wanted to contrast here some of this sort of dynamic behavior that's difficult to predict, right? So this is a period of time when there was a lot of rainfall, a lot of heavy rain events. 2011 in particular, that was our record year of rain, and certainly in the Lehigh Valley, 71 inches. As far as we know, we have about 50 years of record. And you see the number of times in this time span when the river, this is flood stage up here, but when the river, say, exceeded this 15-foot mark, right? Whereas down here in the more recent time period, and this actually continues, we've not had much action on the river in the last year. There was a peak in early March that came up to about 12 feet. But you see in this time span, which is the same length of time as here, it only hit 15 feet once, and we never saw anything up here near flood stage. So just to point out some of the variability that we have to sort of try to understand with these systems. There's one, so this is the back-to-back 1-2 punch of Irene and Lee it was right at the beginning of the semester that year, because we canceled class for a while, and that was fun. We all had plenty of time to go down and look at the Bushkill and the Delaware and see what they were doing. Here's one I want to point out because it's sort of like the opposite end of the spectrum. That 24-hour rainfall is the highest on record in the Lehigh Valley. It's over 8 inches, which is more than a 100-year rainfall, okay? Not much of a storm, right? Or not much of a peak flow or a flood. But look at what the conditions were prior to that, right? Very dry period, and all of a sudden we get this big dump of rain. So there's no 1-2 punch, there's no setup. And yes, we got a pretty good peak, but nothing like we might have gotten if that had occurred somewhere over here, right? All right, so let's move on here. So and here's the longer term record. So there's a thing that's different here. This is a plot of daily flows, right? At 1 day, 365 data points or 366 for each year. The next plot, and I think most of what Dru was showing, these are an annual, so you take the entire year of data and what's the peak flow for that year, and that becomes the data point that's on this chart, right? So these aren't consecutive. These are assumed to be actually independent. So 2005 and 6, although those are consecutive years, statistically we assume they're completely independent and one's not related to the other. we're trying to understand this graph and put some probabilities on it and understand, well, how big were these floods versus what we now have as a flood of record, Connie and Diane in 55. And, I just want to point out that, you can have a clump of 3 really high values, and you can have clumps of low values too, right? And nobody gets super excited about those, but statistically, they're as weird as those, right? Okay, so why quantify flood probabilities? Well, there's a very practical reason, and it's the National Flood Insurance Program that I always remember that date because it's about as old as I am, so it's about 50 years old almost, right? So it was passed after we had a big tropical hurricane event that went through both Florida and Louisiana and caused tremendous damage. And the idea was that, well, we got to figure out how to provide insurance to people in these areas that are vulnerable, high hazard areas. It's got to be affordable. But to do that, we're going to make sure that governments adopt and enforce floodplain regulations, right? So then the question was, well, I think I might have missed that part, but when we say the floodplain, that's when a geologist says the floodplain, that's different than an engineer who might say the floodplain, right? But the reality is there's floodplains and then there's floodplains. It depends on how big the storm is, how much of that it occupies. So what floodplain was the question? And what came out of a group of very notable scientists at the time who got together in late '68, and they met in Chicago, and this fellow named Gilbert White, who's sort of thought of as the father of floodplain management, was in charge of that group, and they came up with the 100-year flood, which they called the base flood, as a reasonable compromise between some things that the Corps was doing for large flood control structures, dams and levees primarily, and what the town or municipalities would be doing to deal with stormwater. It was felt that 100-year was a kind of a nice middle ground, because we can always make things bigger, right? But there's a cost associated with that, so we don't want to necessarily do that. So that's what this is not the Gilbert White that some of you might have read his natural history of Selborne. That was a few hundred years before. This guy was a geographer. He lived to be about 100, I think. Died in 2000 something. Anyway, so the 100-year flood was nomenclature that was used, but even then that committee had arguments about whether they should be calling it that, because really what they meant was the 1% annual probability flood, and they knew that. So it's the flood based on the historical record, and we'll talk more about that has a 1% chance of occurring in a given year. But previous to that, the committee's work, this fellow Fuller, who was an engineer, and apparently not very good at communications, as some of us, I suppose, are, had kind of figured out that, well, mathematically 1% annual flood, if you put 1 over that, you get 100. So roughly, that should correspond to about 100 years in time. But anyone who's looked at stream data knows that it doesn't work that way, right? Okay, so why is this particularly relevant is that people like me live near these things, right? And anyone who lives in Easton and places like that. So this is the Delaware River, this is Regalsville, that's my house right there, right? And I hope this map is accurate because it says that over on the other side of 611 is the edge of the 500-year flood. Probable maximum flood, I'm probably going to get wet. And the 100-year flood is over here. So we have this mapping that is a direct result of the National Flood Insurance Program because it determines who needs that kind of insurance and who doesn't, right? So if your dwelling is in here and you're trying to get a bank loan, you're going to have that insurance, right? You don't have to if you own this outright. It's up to you what you do, right? So that's, how do we create these is kind of where I'm going with this presentation. All right, so I'm lucky because if you go downstream to where the light is, right there. We only have one light in Regals. I love that about our little town. But down there, most of the town is within the 100-year flood area, right? So we regularly get flooded in like 2004, 5, and 6. Before I moved there, this whole area was underwater 3 years, or close to, not the whole area, but parts of this were underwater 3 years in a row. So this is important. All right, so more about the flood. I think I alluded to some of this. So here's NOAA, I think, and two of everything on board, and somebody from the clouds asking, this survey will only take 5 minutes to help improve future floods. So importantly, 1% probably doesn't say anything about when the floods occur. If we had 10,000 years of record, and we don't, it might be the case that on average, every 100 years or so, we got one of these, right? But we don't have that kind of time scale that we work with. So we know, everybody knows from personal experience, that weather varies irregularly, right? We don't often get a big snowstorm in the middle of March, but it's not that uncommon. It probably, I mean, I was ready for spring, but I wasn't too surprised, right? Things like that happen. The 1% flood does not occur once every 100 years, right? It will clump sometimes, and sometimes it'll be farther apart. And I think if we had enough perspective in time and lived long enough, you know, we might start seeing that relationship a little bit better, but we can't. The other piece of this that's important to realize is that we are assuming here that what happens this year and next year are completely unrelated to each other, right? They're independent, right? All right, so how do we go about, given that, how do we go about creating some sense of these values, these numbers, like the plot that we showed of the annual peak flows? So we assume this is countrywide. We use a particular type of probability distribution. I mean, you know, the details are not important. It's not a normal or Gaussian symmetric distribution. It has skew out to the higher values. What we do is we take whatever data we have and we fit it to some distribution of values, okay? And sometimes we have as much as 100 years, and that's considered a nice long record. One of the things that so we're eventually going to be predicting what's the magnitude of the 100-year flood and the 25-year flood. That's what this process will do for us. But built into that is this idea here. There's a term called stationarity, which basically means that, yes, we have variability. Things go up and down. But if you take a long-term view, the mean, the average is roughly the same, and the envelope of the ups and downs isn't changing. It's not starting out like this and then getting bigger and bigger in terms of our variation. And it's not trending upward in any way. If you're using historical data and fitting distributions, you basically have to make this sort of assumption, right? And I'll talk soon about what does that really make sense in the times that we live in. So when we're estimating these kinds, so 1% would be what we typically call the 100-year, this would be the 500-year, this would be the 25-year. You know, most of our information is in the middle of our distribution, right? So there's some kind of a set of values that occur frequently. Most of our data is there. But then out in the high values is some of our data, and that's where we're going to grab the information from our fit and say, okay, this is the 100-year value over here. Now that's fraught with uncertainty, because when you're up there in the upper tail of a distribution, you have less background support for that part of the curve, right? The middle of the curve, where most of our storms occur, our floods, we've got good data support for that. We have less and less the farther we get out. This is something nobody really ever tells the common citizen. So the next thing we do, okay, so this allows us to get these values. So we say like the 1% flood is 300,000 CFS or something, right? Then we have to map that, right? So one thing I do have here, and you can pass this around, is something called a flood insurance study. It has some of the sort of mappings that come out of this process here. And I didn't want to get too down into the weeds on all of this. But basically, we're going to have a model that basically models the cross-section of our river valley. And for a given value of flow, let's say that 300,000 CFS, how much of that valley does the water fill, right? So we have to map that number, that 300 CFS, to a physical location. That requires a model. It requires some surveyed cross sections. When I showed the map earlier of Regalsville, there were a couple cross sections marked, so that was done as part of this process. We need to know about the slope of the channel and the roughness, or whether, say, it's a sand bed versus rocky versus trees. That will affect where this the surface will model. Okay, so after going through that process, we can develop these inundation maps that I showed you, what's called the firm map, flood insurance rate map. Now, okay, so people often wonder, well, we just had a big flood, let's update the maps. Well, it's not really, that's not that practical. We don't do that kind of thing. It's a big effort to do all this. Thinking about resurveying cross sections, getting a team of experts to run these models and things. It's not something that can happen every couple years. However, on the Delaware River, it hadn't been done since 1984. So all these big floods we were having, using this old set of numbers based on the historical record up to 1984, was getting pretty outdated. So there was a big effort, mostly led by New Jersey, to get this reanalyzed. And so in 2008, this report came out. So we have flood magnitude and frequency of the Delaware River. Northampton County's, I think the date on that report is 2011. So that's been updated pretty recently as well. But again, we're going to get more big floods, and if they're really big, or even if we don't, if we get fewer big floods, maybe we should update the numbers too, right? But it's not practical to continually be doing that. All right, so what is the results of this report look like? So here are the lines. So the 1% flood, and I don't know if that's the same number that Drew had on his. This is Regalsville gauge, so I think it was a different gauge actually. Was that Belvedere that you showed? Okay. So Regalsville, besides being where I live, is the first gauge that's downstream of our Lehigh Valley area. So it would be probably the logical one to look at downstream of the Lehigh Valley. So the 1%, or what we typically call the 100-year flood, so that pumpkin flood lands just about right on top of it. And I think it was the 2005 flood, which was close to a 100-year flood. But the other two certainly weren't. They were big floods, but they weren't back-to-back-to-back 100-year floods. Absolutely not. Ivan here was close to a 25-year, and I think that came out about 70 years for the 2006 flood that was due to just a whole bunch of rain that fell that June, if I have my years right. Okay, and then you see down here 2011, Irene and Lee, somewhere between a 10-year and a 25-year, right? So this is how the process we use to put values on these events in terms of probability, right? So then that gets translated to maps. The other thing I didn't mention here about updating, oh, here it is, right? People would kind of freak out if that line kept moving back and forth under their house, right? So that's another reason why it's not something you just jump into. Okay, so the one point I wanted to make here is that I think there's great certainty that that's a pretty darn good value, but as you move up, there's less accuracy or less certainty that that's really the 100-year value, okay? Because we have less information out there in the end of the distribution. Yeah, I wish I had. It's not a 500, but it exceeds the 100-year. Yeah, I don't have that line up there. So then the result of that is this kind of a map. So you see, this is the update. And by the way, I should have put a link here, but this is all now. Used to be you had to find the right paper copy, and it's all online now. It's very easy to get to. I should have put the link here, but you can get these nice color maps of just about anywhere in our area anyway. So you see, this is the blue is what we call the 1% flood. This tan is 0.2% or the 500 year, right? And so that extends out, because this is a flatter area, that extends out into downtown. But here, we've got a steep slope, so the difference between the 100-year and the 500-year line is not great, right? There's a very steep slope on the south side of College Hill there. But as Dru pointed out, when we get that backwater effect, now this is all due to flooding on the main stem of the Delaware. That extends all the way back. That's the public works yard, right? So that's full of water back there. Okay, I want to point out a couple things here. And one is that, okay, so what we've plotted here is the edge. So that line is the 1% line, right? So presumably, areas of ground that are closer to the stream, and this will depend on the slope of that terrain there, have a higher probability, right? They're closer to the river, right? So FEMA maps don't include any of that information, but they could easily, right? So this does depend on slope, so this is just a schematic here. And if this doesn't make any sense to you, look at the comment, because it's a pretty good one. The Beaver says something on a floodplain, preferably, versus riverfront, others might say. So in the 100-year floodplain, schematically, it's not unreasonable that there's also a 10% floodplain. So if in fact your house is there and not there, you really ought to be paying more for your insurance than this person. That's what the science would say, right? But you don't. It's anywhere in there, you pay a particular rate. And it's just something to be aware of, it, this house versus that house. Okay, let's take a break. Quiz time. Anybody know the Lehigh Valley's hydrologic condition is currently normal, drought watch, or drought warning? Drought watch, that's right. All right, they backed it off, and with the snow melt, maybe we'll get back into the normal range here. We'll see. That's a nice thing about snow, although I'm not a big fan of snow in March. It's really good for the groundwater in our rivers. Okay, we've got, and I'll show you this, a really nice long record of rainfall in New York City at Central Park. Anybody want to guess how many of the top 10 wettest years on record have occurred since 2000? So roughly the last 10% of the record should have, if everything's sort of average and hydrology and rainfall's not weird, well, you'd say, well, it's probably 1, right? Right? But it's the answer C, 4, right? That's interesting. Could be chance, but maybe not. How many of the 20 largest flows on record for the Delaware River at Easton have occurred since 2000? It's 8. Right? I mean, why would I ask you questions if there wasn't an interesting answer, right? It's 8. So there seems to be, now, having said that, we're currently on the drought end of things, not on the wet end. There seems to be this trend towards more rainfall and more flooding going on. So this is the dates from big floods on the Delaware River at Easton. And this goes back over 100 years. Right? And you see a bunch of recent numbers here, particularly 2011. Now, I didn't count all of these. For example, I didn't count this and this as separate, right? They're only 4 days apart. But still, you come up with a big number. What's going on? Well, other folks than I have shown by looking at national records of rainfall over this 50-year period that we're getting more rain. Okay, this is annual precipitation. But importantly, particularly in this northeast area, we're getting increases in the bigger storms, right? So this is over this 50-year time period. It'd be interesting, to see this updated. We have almost another decade of data now. But we are in an area where there has been a pretty significant increase in large rainfall events. This is actual data. I just put a 5-year, what's called a moving average on this to smooth it a little bit. This is the actual rainfall record from, this is Belvedere Castle in Central Park. That's where the data is collected. This is a really long record from Central Park. And it seems like there's been this odd shift. Sort of declining, and then it jumped up, and it's sort of staying up there. I can't tell you what it'll look like 25 years from now. Maybe it'll bounce along on this. I don't know what's going on with this thing. It's dying or something. That's what happens when kids get a hold of your laser pointer. Do you have that one? Is there one on here?
There is one there, yes.
There it is. Well, I got two now. So point is, there's a shift that's happened. I can't tell you if this is going to continue or is something that goes up and then goes down, but it's certainly interesting. I've looked at specifically at the Lehigh Valley data and looked at days with lots of rain and weeks with lots of rain, and there certainly seems to be, particularly in this last 20-year period, more of these big rainfall days and weeks, right? It's not, it's going up, up, up for the weeks with greater than 5, definitely gone up for the weeks with greater than 7. The blue went down a little and then up, but I mean, that's how real data is. It never just does one thing, right? So it's raining more, at least for the time being. The other part of what's going on, I think you all are familiar with, and many of you have lived in this area a lot longer than I have. This is the Frost Hollow drainage, which is up over the hill from Lafayette, where the new golf course is over there. And this is what the edge of the outlet of the stream looked like after Ivan, which is, it isn't supposed to look like that very often, right? And whoever lived there was nervous, I'm sure. But look at the changes, and this is based on aerial photography, in that small watershed, right? So it's very dramatic. So at small scales, we have things like this going on that are changing our hydrology of our streams. Whether that's happening yet on the Delaware, I'm not ready to say. All right, so I'm close to wrapping up here. So is this the new normal? We know that precipitation is highly variable, and that's something we're always going to live with. But our climate does appear to be trending, and what we're seeing so far is that we live in a wet area, humid climate. We're getting more water and more of it in these heavy, large events. So there's this piece where, as we develop the landscape, we decrease infiltration generally, so we get more runoff per unit of rainfall, so that would exacerbate this additional rainfall that we're getting. It's complicated, though. When you go to look for this effect on a big trunk river system like out here in the Delaware, which, like I mentioned before, there's a lot of this going on in the Lehigh Valley, right? But the Poconos and those other areas, there's some development, but it's not to the intensity that we're seeing here. So it's hard sometimes to see these impacts, harder than you would think. All these other effects muddy the waters. That was a pun. But construction of dams. We don't have dams on the main stem. Our river's famous for that, but there are dams on a lot of the tributaries. So, and they came in, in the 50s or the 30s in some cases. So that, when you look at the long-term record, that's going to have some impact. Power plants will affect the low flows and so forth. Okay, but I think the thing that we have to be thinking here is that when we look forward and we say, oh, the 100-year flood is whatever, well, it might not be anymore. That 100-year value that we developed was based on the last set of the data that we had, the historical record. But we're trying to predict the future here. So it's quite possible that the next century's 1% flood will be bigger and maybe will happen more frequently than we think, with a number like 1% attached to it. We do know for sure, and this is, I think, the realm of the folks that work here, that flood losses are definitely increasing. But that's a human problem as much as a science problem. So what to do? I have a couple of ideas. Some places, New Jersey in particular, is adopting basically like a factor of safety. They have a base flood elevation which includes a 1-foot addition, which is often called freeboard, that they just add on top of it, just because that's a way to be resilient about the future, where we think the floods are going to be larger maybe and more frequent. So that's not a bad idea. I have some ideas here about what floodplain maps should look like to kind of better communicate really the risks that people are assuming. So the idea of having a little bit of a buffer zone for the 100 to 2 year, showing some of these higher probability zones inside that, What we just have that blue flood, 100-year, 1% floodplain.